Time for us to lay some groundwork for another conservation law, the conservation of momentum. And we won't do many examples in this video, but in this particular video we'll lay the groundwork. We'll talk about what momentum concept means, how it's calculated, talk a little bit about force, and talk about impulse. It's kind of a technical physics term, but you'll not have any difficulty with it. So first, our definition: momentum is the quantity labeled with p, small p, and it's easily found by taking mass times velocity. Is momentum a vector? Yes, and it has a direction the same as the direction of the velocity. So it is important, and there will be situations where we'll have to handle momentum as a vector and deal with components in two perpendicular directions, an x component and a y component. But momentum is a vector. It's easily found by taking the mass in kilograms and multiply by the velocity in meters per second. That's our standard metric unit. So we've talked in the past on how F equals ma is used to calculate acceleration. A little confession here: F equals ma is not Newton's original second law. Instead, what you're seeing here is Newton's second law. And we're not doing calculus in this course, so we'll approximate calculus a little bit here. But the force, the net external force, causes a change in the momentum. Again, delta is change, so momentum final minus momentum initial, and that occurs over a certain time interval. If someone tells you the final momentum and the initial momentum, and those directions going to be part of that, you subtract those and divide by the length of time for that change to take place, then you would have the average force, the net external force, applied to the object. So this is Newton's second law. Net external force causes a change in momentum. Now, if the mass is constant, then we get to F equals ma quickly from this. You could try substituting mv here and let the delta be applied to the v and the mass be constant. So F equals ma is contained in here, but this is a more general relationship. Just talks about the change of momentum, so the mass might be changing as part of the situation that is undergoing here. So F equals delta P over delta T. The average net external force is calculated by looking at the change in the momentum divided by the time that is done. So let's go a little bit further with this. If the net external force is 0, then we're going to have a situation where F is 0, delta P must be 0, and the way delta P can be 0 is if the final momentum and the initial momentum have the same value, that the final momentum equals the initial momentum. Then this subtraction comes up 0, delta P is 0, and that matches the 0 over on the left. Now, again, very important, this force that's here is the net external force. We don't consider internal forces, and we consider the net external force to do this analysis. But if that's 0, then the final momentum equals the initial momentum. This is conservation of momentum. And it is worth pointing out that it's a little broader conservation law. Applies to more situations than conservation of energy. When we have kinetic energy, it's sometimes not conserved in a system. If we have a loaded spring that launches a projectile, that kinetic energy is going to change. It's going to gain energy from the spring. But we can apply conservation of momentum. If two people on ice are standing side by side and they push on each other, they had no kinetic energy to start with, but they move away from each other with some kinetic energy. Their momentum, net momentum though, is still 0. One will have a positive momentum, one will have a negative momentum. Now, conservation momentum, a little broader law than taking a look at energies. So, situation where a couple of vehicles, unfortunately, are going to hit each other just on the bumpers, and we have a momentum for car 1, a momentum for car 2. If we total that up, we've got the total momentum before some event takes place. Later, we have a different velocity for each car, and we can again total up the two momentum values. We'll find that P1 plus P2 before the collision, and that P1 is momentum of car 1, P2 is momentum of car 2. But the sum of P1 plus P2 is the same as P1 plus P2 after the collision if friction can be ignored. Why does friction have to be ignored? In order to conserve momentum, we need zero net external force. Friction would be an external force in this system. So if that's the case, we can say momentum is conserved. People who analyze accidents take into account the friction on the roadway and do take into account some modified conservation laws once friction is estimated. So this conservation momentum does have application to the real world. We don't totally need friction to be zero. As long as it's small, then we can use conservation momentum. Now, the situation of impulse, if we rearrange this just a little bit, multiply by delta t on both sides, then we find we have force times delta t. The average force over the time interval multiplied by the time interval. Perhaps our average force is 20 newtons, and we have 10 seconds of that. 20 times 10 would be an impulse of 200 newton seconds, and that will equal the change in the momentum. So it's important that you realize this F has to be constant in this calculation over the whole time interval, or we use an average value over the whole time interval. That's probably a better statement. But F times delta t is the impulse. For those science fiction fans, maybe this reminds you of something on the Starship Enterprise. How does it get around the solar system? I'm not going to tell you. I'll let you ponder that, and my students I'll tell in class. So here's a graph of an actual collision. When the contact first starts, there's very little force between the two objects. And we have increased contact here as the collision deepens, and we get a maximum force of interaction of maybe a baseball bat and a baseball. And then the ball leaves the bat, less and less contact. Very complicated. We're not going to look at the change of force. Instead, we're going to say, what's the effective force? What's the average force over the time interval? That's what we'll use in our impulse calculations. So this moves on into collision. So I'm going to stop the video here with this just little introduction to momentum and force and impulse. We have a new quantity, momentum, that is found by mass times velocity, and this force is the net external force related to the change of momentum over change of time. Multiply both sides, and we get impulse that tells us how the momentum is going to change. The force and momentum are vectors. The direction of the change of momentum will be the same as the direction of the force. So keep reading with that, ask some questions.